Have you guys ever been diving? If yes, you definitely got told to do a pressure equalization. And this is because of the gravitational pressure, which rises when getting deeper. And to understand that, we will first have a closer look at the two words that describe this phenomenon of a rising pressure in liquids. So what do we got? First, we got the gravitation. And gravity is always something that pulls objects towards each other. And this is because masses attract each other. If you don't remember that anymore, just click on the link in the presentation to refresh your knowledge about Newton's third law. Second, we need to talk about the pressure. And as you all know, pressure is the force applied perpendicularly to the surface of an object. But even if you don't remember that, no problem, just click on the link to get to the fifth lesson. But the gravitational pressure actually behaves a bit different to the pressure we're used to. So the gravitational pressure is defined as the pressure caused due to the gravitational force of the column of a fluid, which means of a gas or a liquid, on top of a certain object. But what does that actually mean now? To make that clear, we'll just have a look at some examples. So let's imagine any random dude. If that dude would be standing on top of a mountain, the gravitational force would be way lower than if that same dude would walk around in a valley. And that increase of the pressure we can even feel when driving down a mountain in a car, and all of a sudden you feel a certain pressure on your ears. Or we can even feel the pressure on our ears getting less when an airplane takes off. So let's take that same dude and let him put on his diving gear. He will definitely feel that the gravitational pressure at the bottom of a sea is always higher than on the surface of that same sea. And the clue about that is that the gravitational force exerted by the particles building a column on top of that dude is obviously a lot higher when getting deeper. So let's get straight to our first example of the dude feeling a lot higher gravitational pressure on top of a mountain compared to the pressure down in the valley. And for that, we should have a look at the profile of our dearest Earth. And as we all know, the Earth is surrounded by its own atmosphere. The outer part of the atmosphere is called the exosphere, which is the transition between the atmosphere of the Earth and outer space. It is marked red in the sketch. The exosphere starts at about 500 kilometers above the sea level and ends approximately about 10,000 kilometers above the sea level. Further, it is well known that the atmosphere contains a lot of particles, unlike outer space, where there's basically nothing but vacuum. At least in between the planets and stars and all the other strange stuff hanging around. Each and every particle now has a certain weight, which then must exert a gravitational force. And all the particles above a guy standing on Earth hence exert a gravitational force on that guy. If that same guy climbs up a mountain or takes off in an airplane, he has less particles on top of himself than before. Therefore, the gravitational force exerting on his surface must decrease. And for we know that pressure is calculated as the force exerting on a surface. And for sure the surface of our dude does not change, but the force exerting on him gets less. And this is why the pressure on that dude must decrease as he climbs up the mountain. But this is rather an outlook to what we'll be talking about in the next lesson. So as I promised you, today things are getting deep. So let's get right to our second example. The example of the diver. When the pressure decreases when getting up a mountain, it is on the other hand easy to understand then that the pressure rises when getting lower, just like our diver does. So when the diver dives deeper and deeper, the column of water on top of his head rises and rises, which causes a higher and higher gravitational force, exerting on his surface from above. And that means that the pressure applying on our diver is increasing. But if the diver is keeping its depth and moves only horizontally, the column exerting on him doesn't change at all, which is why the pressure stays the same everywhere in the water, as long as the diver doesn't get up or down. So let's take a closer look at our diver. As he dives down, the pressure on him is increasing, which we know. And that means nothing else than that the forces exerting perpendicularly on his surface are increasing either. And as we have seen in the regular lessons, pressure is observable when pressure differences are occurring. So if the pressure from the outside is increasing more and more and the pressure on the inside of the diver stays the same, the difference between these pressures increase, which causes damage by the diver. Amongst other issues, that occur when being exposed to a high pressure, the eardrum of the diver will get damaged. We can imagine our eardrum as a thin membrane like this red line. If the pressure P2 from the outside increases, the membrane bends to the inside more and more, until it rips due to the increasing pressure difference. But this is just how an eardrum would behave if the diver is not doing a pressure equalization. Luckily, divers know about that issue, so that every diver is doing the pressure equalization after just a few meters. The diver has now, as we know from the regular lessons, 3 options to change the pressure in his head to equalize it to the occurring pressure on the outside. If you don't remember the options anymore, just have a look at your 6 nice things to know about pressure worksheet. So I want you to write down the 3 options and just upload them in the assignment. Further, I want you to decide which option the diver should take. Post your decision in the assignment either. And write down how the eardrum would look like after pressure equalization. But why can we drive down a steep road without doing a pressure equalization for about 50 to even 100 meters? And why does the diver need to do the pressure equalization that often? Well, the answer, or at least part of it, is density. The density ρ of an object or a system is defined as its mass per volume. A higher density means that a certain object contains more particles, even when having the same volume. 1 cubic meter of water is about 1000 times denser than 1 cubic meter of air, which means that if the diver dives down 1 meter while the dude on the mountain is walking down 1 meter, the diver shifts a lot more weight on top of his head compared to the climber walking down the mountain. Using the concept of density and the formula to calculate pressure we are familiar with, we will be able to calculate the gravitational pressure that exerts on a diver in a certain depth. And for this, we first have to remember that the pressure is defined as the force exerting perpendicularly on a surface. And for we're talking about the pressure caused by the gravitational force of the column on top of an object, the force we're talking about is the gravitational force F equals mg. But since we don't know the mass of the contained matter in the column, we need to replace the mass. And for that, we're using the density. We know that the density ρ in a system is defined as the mass divided by the volume. And to get a mathematical expression for the mass, we rearrange the equation by multiplying both sides with the volume. And now we can plug in that expression for the mass into our formula for the pressure, which gives us that the pressure P is equal to ρ, the density, times the volume, times the gravitational pull, divided by the surface. And in this final step, we now need to think about how to get the volume of the column. And to get this, we just need to figure that the volume of a certain column is nothing else than the base surface A multiplied with the height h of it. Now throwing in that expression for the volume into our formula, we can see that surprisingly the surface A cancels out, which means that the pressure in a liquid is not depending on the surface of an object at all. And this gives us our final equation, which says that the pressure P in a fluid equals to the density of that fluid times the height times the gravitational pull. And since the density of a medium is constant, as well as the gravitational pull, the gravitational pressure is depending only on the height.